Gordon Semenov, who will be talking to us about graphene.
Okay, thank you, David, and I thank the organizers for the opportunity to visit here and to speak, the organizer who is present. So today I'm going to talk about a certain D-brane construction of a system which is designed to resemble graphene. The resemblance isn't exact, but I hope you find it nevertheless interesting. So for those of you who don't know what graphene is, I'm going to give a brief review of it to tell you some of the nice features that it has, and to set the stage for the things that one would like to construct. And then I'm going to talk about a holographic model of 2 + 1 dimensional relativistic fermions. And this is a rather simple one as holographic models go. I would say low-tech holography, which perhaps matches the low-tech nature of graphene in some ways. And then I'm going to try and draw some connection between the two. In particular, to use this model to make some predictions for what experimentalists might look for in graphene, which is kind of nice because doing string theory for many years, I've never really ever before had the opportunity to make a prediction for an experimentalist. So that's one of the real pleasures of doing this, and maybe somehow I can transfer some of this pleasure to you. Okay, so what is graphene? Well, it's basically 2 + 1 dimensional, or in condensed matter parlance, 2-dimensional array of carbon atoms that sits in a hexagonal lattice like this. And so you can think this is a flake of graphene. And it's related to other carbon materials, which actually form the basis of nanoscience for many years, so-called fullerenes and nanotubes. These were discovered in the 1980s and the 1990s, and after the year 2000, graphene was made experimentally. It's kind of interesting that the complexity of the material seems that for some reason this is easier to find than this, and this is easier to find than this, even though this has been with us forever as the flakes that make up what's called graphite. Just to show you a real picture of the stuff, here's an electron microscope picture of a sheet of graphene. It looks a lot like, well, what in North America we call a chicken wire fence. And in fact, it looks interestingly close to the stick figure on the previous page, in that the little dots here really are the carbon atoms. This is a real picture of it, and the sticks between the dots are really the covalent bonds that hold the thing together. And the one thing to remark about this rather nice picture taken by the team electron microscope group in Berkeley is how clean the material is. There isn't a defect to be seen. There isn't an impurity to be seen. This is a cleaned up sample, but the fact that it even cleans up this well is unusual for condensed matter. In fact, graphene comes fairly clean from the beginning, from its rather low-tech way of making it, and it's not hard to tie up dangling bonds. In fact, there are very few in these carbon materials. So it comes out rather nicely. And the one thing about it is that it's never really flat. It's never really plate, or it's always a little bit corrugated. And you can actually see that in this picture by the slight variation in the intensity. And that simply comes from the fact that parts of it are a little farther away and parts of it are closer to the electron microscope.
Let me just say, I'm having problems seeing it as hexagonal, in the sense it looks like this rectangle.
Really?
No, I mean, I realise I'm being stupid. I realise I'm stupid, so I'm probably missing something. I mean, is it the dots themselves? Are
1, 2, 3, 4, 5, 6.
Oh, so really those dots are hexagonal?
Yeah, and those dots are actually carbon atoms.
I need my eyes doing
it's
again. I mean, they look quite round to me, but okay. Sorry.
So this is a scale of, well, let's see, that's probably a centimeter, and it's 1.4 angstroms. So magnification of some large factor.
Yeah.
Okay, well, the stuff was produced in the lab in 2004. The first, I guess it's a little bit disputed, but the first reliable, low-tech, nice, easy way to produce it was found in 2004 by these researchers who work somewhere, actually just down the road from here somewhere in Manchester. At least from a North American resolution, it looks like almost the same place as Cambridge. And that sort of started a firestorm of activity in the condensed matter community. And the activity comes from, well, the fact that, number one, two-dimensional crystals were not supposed to exist. There's a chapter in Landau and Lifshitz that explains why they don't exist. Number two, it had rather interesting electronic properties. And number three, it's really easy to make, because all they did is take carbon, so some kind of black substance in a bottle, rub it on a substrate, and then the legend goes that they used Scotch tape to kind of thin out the carbon that was rubbed there, so that here and there you actually had a monolayer of the stuff. And then they could identify the monolayer just optically using an optical microscope, because they realized the pieces that were monolayer-like were angstrom size, so you could see them under an optical microscope, and they were just a different color than the rest of the stuff around. So it was kind of easy in the end. And I don't know how much truth there is to this. The legend goes that this was all done during, in their lab they had a Friday evening session where they brought some beer and were allowed to try anything they wanted that sort of didn't have to follow the experimental routine of the lab, and this all happened during one of these Friday evening sessions. And I thought that such a wonderful idea that maybe one could implement it in our theoretical group, but somehow it doesn't work so well in theoretical physics. Okay, the electronic structure of the material is pretty easy to understand. The carbon atoms that you think of sitting at these intersections have 4 valence electrons. 3 of those electrons are soaked up into very strong covalent bonds with the neighboring carbon atoms. Those are among the strongest bonds in nature, which make the material very tightly bound and is somewhat responsible for its very clean properties. The 4th valence electron is not used in this bonding and is more or less free to move around and becomes the electron that's active in the electronic properties of the material and the one that's of interest to us here. And things could be a lot more complicated than they turned out to be. For example, one of these cells is a benzene ring, and that extra electron in benzene has a fairly complicated structure, a kind of a resonating valence bond structure. It turns out for some reason in graphene, when you put a bunch of benzene rings together, basically, the electronic properties are much simpler, and in fact are fairly well modeled by a so-called tight binding model, where you just think of electrons as living in loosely bound orbitals at these points, and you make a Hamiltonian which describes tunneling between of electrons between neighboring sites. The density here is 1 electron per site, and an electron has 2 spin states, so in a sense the electronic states are half filled here. The hexagonal lattice you can think of as a it's not a Bravais lattice itself. If you take one of these translations and do it twice, you don't come to another lattice site, but you think of it as a superposition of 2 triangular Bravais lattices, which here are written by black dots and white dots. And then the simple tight binding model just describes hopping between type A, lattice type A, and lattice type B, something like this, with a hopping amplitude. And all these numbers are fairly well fit. Well, the lattice spacing is about 1.4 angstroms. Hopping amplitude is around 2.5 electron volts, which sets the energy scale. And all of this was known a very long time ago because it was basically used as a starting point for the electronic properties of graphite. Right? Since graphite is made from graphene flakes, of course you first solve graphene and then you somehow stick them together to make the much more complicated structure of graphite. And this came from the 1940s, really, when graphite was first used in nuclear reactors as a moderator. For some reason, it was interesting to know what its electrical properties were. And I worked on this a long time ago, in a sense, what I like to think of as 20 years too early. But it was realized that, well, this model was solved, and the solution is kind of interesting. It's trivial, right? Just free field theory. You solve it by Fourier transform on the lattice. So here's the Fourier transform. It's useful to treat the A and B sublattices differently. That already gives the Hamiltonian a kind of matrix structure, which is starting to look Dirac-like. Of course, that's not really enough because just about any lattice can be divided into two sublattices, and very few of them have Dirac electrons in them. What you need is that these off-diagonal elements here are essentially complex. This has a reflection of particle-hole symmetry, and it has two bands that are identical, positive and negative energy bands. You'll get Dirac electrons when these bands intersect at points. Since these are complex numbers, complex function of two real variables, the bands intersect when those functions are zero. Two functions of two variables are generically zero at points, and so that's the thing that you need, is that this is complex. That's the thing that doesn't happen on a square lattice, for example, with the most naive model where it's real. So that's the thing that's special about this triangular lattice. This turns out to be complex. The bands look like this, and they indeed do intersect at discrete points. In fact, a picture of the band structure looks something like this. So here's the positive and negative energy bands, and they touch at some points. You notice that the points are black and white here. That's because the white ones are related by reciprocal lattice vectors. They aren't inequivalent. Similarly, the black ones, so there are actually two inequivalent ones for Brillouin zone. Remember that the lattice, the neutral lattice, is half filled. Half filled means half of these states are filled. Just by symmetry, that means that the Fermi level is actually at these points. That's sort of a second miracle. So in neutral, sort of zero temperature graphene, you expect all of these negative energy states to be filled, positive energy states to be empty, and the Fermi surface is right there. And then for low energy excitations near the Fermi surface, the spectrum looks conical. And in fact, if one goes back and analyzes the Hamiltonian at low momenta, Taylor expands near these degeneracy points. It's not only conical, but it has a full 2+1 dimensional Dirac Hamiltonian. Right? So the electrons are really Dirac electrons if you consider small energies down there. And so being a field theory, here's what we do. We put a cutoff. In other words, you throw away all the ugly parts. And we're left with these nice little relativistic bits here with a cutoff. Two of these are inequivalent. We sort of linearize the momentum space near these points, and we get Dirac Hamiltonians. Two of them, because there were two degeneracy points per Brillouin zone. These look a little bit different, but it's a sort of trivial redefinition to make them identical. And so you get, in a sense, two species of electrons. And I've forgotten all about the spin degeneracy here, so one should add it. Nothing coupled to spin so far. So that's another factor of two. So you have, in the end, four species of 2+1 dimensional relativistic electrons.
What gives you the rotational symmetry? What makes a cone rotationally?
It's just, well, it's not really rotationally invariant back on the lattice, right? There's sort of right. It doesn't really rotate about any point.
Why are all the slopes the same? I understand that far away is not.
Far away it's not. Far away it's just sixfold or whatever it is. But close up it's just emergent. They just become the same.
But you might have expected might be different slopes in different directions.
There might be a higher order.
Yeah, quadratic order probably.
At quadratic order it is, or cubic order, whatever the next order is. But down here it's not. It just
Like cosines when you expand.
Ah,
The same coefficient.
And you might ask, well, also the slope of the speed of light, or the speed of the electrons here is not the speed of light, even though it's a massless Dirac equation. So it has an emergent speed of light, which is the slope of this dispersion relation near the degeneracy point. And that one calls the Fermi velocity. And it is darn fast. It's like 1,000,000 meters per second, but still much smaller than the vacuum speed of light by a factor of about 300. Yes.
What has set that scale?
Just the parameters in the hopping Hamiltonian. So the lattice spacing and then the hopping amplitude. And the hopping amplitude was a few electron volts. I think it's basically set by measuring this speed of the electron and working backwards. It's sort of a fit.
Is that somehow tunable? Maybe if you do some strange things to graphene?
I'm going to argue that it self-tunes a little bit. I don't know how tunable it is. There are other tunable things. This might be the less tunable. It has been tried though, because one thing one could do is stretch graphene. Right? That changes the lattice constant and then changes its VF.
Those two components are not spin components? You said K goes from one
No, this is a pseudospin.
to those.
Yeah. So this is some sort of emergent spin coming from the fact that you had two bands. And it's not really spin because it's in 2 + 1 dimensions. So there's, right, spin is a little bit different in 2 + 1 dimensions. Okay, what else? Let's see, what else I was going to say here. Oh, you might wonder what's the height of this cutoff? Well, it depends how accurate you want to be, because of course the band probably starts curving a little bit right away, but up to at about a 1% level, actually this height can be an electron volt. And an electron volt is a pretty big energy in condensed matter. It's about 10,000 degrees Kelvin. So at room temperature, for sure, all of the thermally excited electrons are well within this cone, way below the cutoff. And for electron hole pairs that are made by photons, up to the microwave or almost visible range is fine too. So that's a pretty high cutoff. In other words, graphene electrons don't even know that they're non-relativistic unless you really do something very high energy to them. And that's rather interesting, and that makes them the most robust of the relativistic electrons that are found in condensed matter. Right? Relativistic electrons are found in other places, for example, topological insulators, or I know the D-wave condensate in high-TC superconductors, but they're there in a much smaller dynamical range, much smaller band of energies than in graphene. And that's one thing that makes graphene very interesting for us, because it's something where one might be able to do experiments, and it is really to some good approximation relativistic. The other thing is, here it looks like one is getting an emergent U4 symmetry, in that if you describe this by a Lagrangian, it is just 4 identical species of relativistic fermions. Not only emergent U4 symmetry, but emergent Lorentz invariants, and in fact not only emergent Lorentz invariants, but these are massless, so it's a conformally invariant theory at this level. Right, so the 2 + 1 dimensional conformal symmetry even. Okay, well, the experiments that really galvanized the attention of, yes?
How's that consistent with the lattice in the sense that surely any, I mean, but the symmetry of the lattice, which is discrete, won't that go through into this thing? I mean, how do you get this emergent? Is it that your energy scale's bigger than the lattice spacing?
The lengths at which you're
Yeah.
interested in studying it are much bigger than the lattice.
Much bigger than the
spacing.
lattice
Yeah.
spacing. I see. Right.
Yeah.
Yeah.
So the original pieces are micron size, which
Yeah.
is already 1,000 lattice spacings. Actually, 1,000 lattice spacings for a lattice gauge theorist is way beyond what they
Yeah.
consider the continuum.
Okay.
So, so the experiments that really got the attention of people were the so-called anomalous Hall effect, which were about a year after the stuff was made, done and published in back-to-back papers in Nature. This was the Manchester group, the Columbia group, and they saw two remarkable things. One is a kind of an offset in the Hall effect, in that the Hall conductivity, which I used to have written here, I don't know what happened to it, goes like an integer plus a half, some number times an integer plus a half, and that's because zero density is right in the middle of a Hall step, something like this. For an ordinary semiconductor at zero density, you have a completely filled Landau levels, and you're actually on a Hall plateau instead of in the middle of a step. Okay, so that was considered anomalous, and that's simply due to the fact that you have massless Dirac fermions, and massless fermions have a Landau level right at the Dirac point. Furthermore, in the neutral material, that level should be exactly half filled, so at neutrality, you should be half done filling a Landau level, which means halfway up a step, just like is seen there rather beautifully. So that's taken as evidence for Dirac fermions. And the other thing is that the steps here are in units of 4 times the usual integer Hall quantum. And that's evidence of the SU4, the emergent SU4 symmetry, the fourfold degeneracy. And that's seen across a very big dynamical range here, right? Steps by 4, not just a few steps, but basically all the steps are in units of 4. Of course, there's more direct ways of looking at the electron spectrum. Yes?
The spin is there even in the usual quantum Hall system, right? So shouldn't that be a factor of 2 rather than 4? I mean, the spin should be doing the same thing in both cases, right?
Yeah, it probably does. I don't actually remember if they're spin polarized or not, but the usual semiconductor probably has a factor of 2. Yeah.
But then relative to that, it should be only a factor of 2, right?
Yeah, it's true. It's true relative to that. If the semiconductor is spin degenerate and not spin polarized, that's true. There are direct ways of looking at the electron spectrum, like ARPAS. So ARPAS stands for Angle Resolved Photoemission Spectroscopy. And what it is basically just using the photoelectric effect. Right? So you shine put a high energy photon onto the system, and it knocks an electron right out of the graphene sheet. And then you look at the kinematics of the process. You measure the outcoming velocity and direction of the electron and the photon, and then you reconstruct the energy momentum of the state that the electron was in to begin with. And so this makes a rather beautiful map of the negative part of the Dirac cone. In fact, it comes out wonderfully, maybe too wonderfully. And the height here, I apologize for the bad, for some reason my new computer doesn't steal pictures very well from PDF files. But this height is something like 2 electron volts. So this is already beyond the cutoff that I promised, that you basically see this conical structure. It's a little bit fuzzy, and the fuzziness comes from the fact that the material's on a substrate, and there is some noise in the background, and so on.
Wait, so on that picture, where would you have expected it to start curving? I mean,
Well, let me see. The height of, in that original picture of the band structure, the height of the neck, in a sense, is around 10 electron volts. So it has to curve by then. And this is already a few electron volts. And so I would actually expect a little bit of curvature, and maybe even there is. I mean, it's kind of a crude picture.
Like the neck would be already at the bottom of the slide.
The neck would be something like here. Right. Yeah. Now, this picture is actually drawn with some assumptions. And one assumption is that the electrons are basically in single particle states. I don't know if actually in ARPAs, if you can remove that assumption. But it is in a sense studying the density of electrons in momentum, energy, frequency and momentum space. And they do seem to be on shell in single particle states. The reason why I bring that up is I'm going to now argue that graphene isn't really weakly interacting. And so the fact that free electrons actually describe a lot of the properties of graphene very well is a bit of a mystery. And the mystery is that you have to explain away the interactions in order to really make the theory fit the experiment. So part of my job here is to explain away interactions, but first let me explain what the interactions are. Probably the strongest interaction is the Coulomb interaction. There is also interaction with phonons and all kinds of other stuff.
Sorry, if you stop bending the graphene, you still get the free reduction, or you start getting something like the metric?
Well, it comes naturally a little bit bent, and that I've just forgotten about here. I don't know how to deal with that. But it is, there's another kind of bending that's called strain, right? Which is more than just corrugating the sheet, actually straining it. And straining it is usually modeled by free fermions, and the strain produces a kind of an axial gauge field that has a different sign for the two species. And that's very interesting. In fact, there are experiments where they strain a piece of graphene so much that they actually see Landau levels of this effective gauge field. It's sort of, so you can change things by bending the sheet, but it's usually modeled by free fermions. I'm not sure that model is good, for reasons which I'm about to explain, simply because Coulomb interactions are pretty strong. So if I put in Coulomb interactions, they look something like this. The speed of the photon is 300 times greater than the speed of the electron, so they're almost instantaneous. But we could put in a retarded Coulomb interaction in as far as it matters, that there's a retardation effect. And the way you would model this, of course, the Coulomb interaction is still three-dimensional, because if you have an electron-hole pair in the graphene sheet, of course, the lines of electric flux that mediate the interaction can come out of the sheet. So the sheet is something like a brane world where the electromagnetic field is actually allowed to escape from the brane, whereas the electron isn't. And so it's still three-dimensional, and a way to describe that is by this sort of a 2+1 dimensional non-local Lagrangian. Non-local because, well, you make it non-local by, say, taking the fourth polarization of the photon and integrating it out. So simply solve the equation for it. It's a Gaussian theory, plug back in, and it makes this non-local stuff. And in a sense, you know it has to be because 3+1 dimensional Maxwell action is scale invariant. So integrating out one of the fields shouldn't change that fact, should still be scale invariant. Whereas in 2+1 dimensions, F times F is not scale invariant, would need a dimensional coupling. So here the dimension of the dimensional coupling just basically comes from this thing. It's the only thing it could come from. And so you get this funny non-local looking theory in 2+1 dimensions. And before I kind of understood this part of the construction, I would have been very suspicious about such an action because it looks non-local, and once you allow some non-local operators, you wonder how you can ever control such a theory, because you can make all kinds of other non-local relevant operators, an infinite number, anything you want, and it should be a mess. But here this descends from 3 + 1 dimensional local theory, so presumably all of those things are okay. I'd say presumably. Okay, so this is how you couple the Coulomb interaction. Now, this top line and this second line separately are Lorentz invariant, and in fact conformally invariant because they're massless theories. However, they have different speeds of light. So when you couple them together, it messes up Lorentz invariance, and it's no longer Lorentz invariant. Moreover, the coupling is strong. A way to see that is by looking at the so-called graphene fine structure constant, which you can think of as an estimate of the ratio of potential energy to kinetic energy. Right, so potential energy you might estimate as the Coulomb energy of a single particle, which is at a state with some wavelength, which is something like this, where you just put the distance in the Coulomb interaction proportional to the wavelength. And the kinetic energy of a massless particle, of course, looks like that. The ratio is wavelength independent and looks just like the usual fine structure constant, except with the speed of light replaced by the emergent graphene speed of light. And that, well, if you just do this identity, and you remember that this constant is something like 1/137, you can see as a fairly large number, because this ratio is 300, and so the effective coupling constant here is bigger than 1. In fact, it's somewhere between 2 and 3. And that should pose a puzzle, because that's a pretty strong coupling. That's like the QCD coupling, in a sense, and you know in QCD, well, QCD is a theory which in the infrared is very, very far from just free quarks and free gluons. Right? All kinds of things happen, and it has a very complex low energy spectrum, whereas here, somehow, this theory seems to still be modeled by free electrons. And so this is something that one should worry about. There are some other interesting features of the field theory that's written here. As written, it's actually a renormalizable quantum field theory. It's not relativistic, but it is renormalizable in that you don't have to introduce any more operators to the action to cancel ultraviolet divergences. I guess that's known explicitly, more or less up to 2 loops, but can be seen. Furthermore, when you renormalize, these terms don't get infinite counter terms. I think you can sort of think of that in a Wilsonian sense, that by integrating out high energy modes, lowering the cutoff, you will never generate non-local stuff like this. So in a Wilsonian renormalization group, these things somehow don't change. That's a little bit counterintuitive. I'm not sure that intuition is really right, actually, but in any sense, in a rough sense, these don't, also in calculations at 1 loop, 2 loops, these don't get counter terms. So just these two get counter terms. And since it's non-relativistic, they can have different counter terms. And the ratio of those counter terms renormalizes the electron velocity. And so in 1 loop, the electron velocity gets a beta function, and it runs logarithmically. And so that should mess up this Dirac cone. There should be some logarithm in it. That's sort of a running electron velocity. Well, that's perturbative, of course, right? I said 1 loop, 2 loop, and here I've argued that the coupling is strong, so maybe it's nonsense for the real material anyway, right? If the coupling is really that strong, this perturbation theory is bad. One should really do something non-perturbative. The other thing that happens is when the speeds of light are equal, if you just by hand put them equal, so raise VF up to C or C down to VF, which is the more likely thing that happens, this is actually a conformal field theory. Well, that's only known again perturbatively up to 2 loops. That it's a CFT, but it is indeed scale invariant, and then there is no beta function for anything, because if it's scale invariant, these two things have to have the same counter term, and so it just by symmetry it looks like a CFT, and indeed that is confirmed by explicit calculations up to a few loops. So what I'm going to do here is take the hypothesis that perhaps graphene, with its strong interactions, this and whatever other messy interactions go in there, together somehow manage to be a conformal field theory with fermion content. That is a fixed point of the RG flow of this theory that's here. That's not a very realistic RG flow because it's perturbative and the theory is non-perturbative, but it does seem to be a fixed point, and so it's an interesting hypothesis to explore. One reason why a relativistic conformal field theory and not some fancy non-relativistic one that's so fashionable these days, well, just this picture. That looks pretty darn relativistic. Right? So if that picture is due to the fact that you're looking at a CFT, it looks like a relativistic CFT, and so that's why relativistic one. And in fact then, that Dirac cone is more or less a consequence of Lorentz invariance and conformal invariance. Right. Okay. Other reasons why a CFT. Well, actually, the logarithmic running of the coupling has been looked for by experimentalists. I mean, of the speed of light. Right? If VF really goes like log of momentum, somehow at small momenta, this Dirac cone should become more pointy than just a flat Dirac cone. One should see some running in here. And this group, this is Alessandro Lanzara's lab in Berkeley. They actually looked for this quite recently with a sort of nice cleaned up graphene sample, and they really don't see this pointiness. Again, apologize for the quality. The actual experimental curve is this one, where the dots are a straight line and the curve is like this. And you can see that up here, it follows a straight line very nicely at low energies. Notice that 1 electron volt is here. This is already where we've been putting our cutoff. And the deviation from a straight line is up here. And I'm not sure they drew this straight line in order to try and demonstrate that there are interactions at as low an energy as possible. They could also draw that dotted straight line to demonstrate there are interactions at as high an energy as possible, just by giving it a little more slope. And you see a sort of deviation from the straight line up near the cutoff. So the running of the coupling really isn't seen. It looks a lot more like something which is conformal in the infrared. It simply goes like omega proportional decay. So that's sort of interesting, and experiments like this on neutral graphene have only become possible fairly recently. And then that's because the older versions of graphene on a substrate, when it's on a substrate, it's very difficult to actually make it locally neutral. What happens, there are impurities here and there, and these impurities cause what's called puddling of the charge. So even if the material is neutral on the average, locally there's always a bit of chemical potential. Right? A bit of positive and negative chemical potential that cancel in the large. Now this chemical potential has been pointed out to be by experimenters isn't that big. The fluctuations in density are something like 1 electron for every 10 lattice spacings. But recently different substrates have been used, and this effect is much smaller. They tell me it's more like 1 electron per 100 by 100 lattice spacings, which actually I would consider a very small fluctuation in the charge density. And so they come to much closer to neutral samples, and this experiment done, well, it's 2011, about half a year ago, something like that, actually is with one of these much cleaner closer to neutral samples. And they really don't see much up here, actually. It's rather interesting. I think they're disappointed by this result and did their best to say that they found interactions in this region, but they didn't really find this pointiness that they wanted to find. Another sort of thing that one can compute, and was done fairly early on for graphene, is the AC conductivity in the so-called collisionless regime, where the frequency is much bigger than the temperature. And here the computation it's quoted is actually at 0 temperature, and where the vacuum speed of light is set to infinity. Right? So the only speed of light parameter is this graphene speed of light. And this computation has been quite controversial for some reasons. Actually, it seemed to be a difficulty in implementing the word identity, which particle physicists should be good at, but somehow in the condensed matter community there was a big discussion about how to do that properly. And the most recent last word on the subject is due to these authors, who give this result, where this constant is something like this. What happened early on is these two diagrams have opposite signs. They contribute with opposite signs, so you can already see that here. And in fact, 3 times pi is about 10, so this difference can be small. And some previous authors somehow found the difference was really small. So C was 0.001, and so corrections are somehow unnaturally small. These people with presumably improved analysis, actually I think calculating the full 2-point function of the photon and making sure it obeys the word identity up to 2 loops, found this result, that the C is about 1/4. Notice here that the expansion parameter is indeed this graphene fine structure constant. So it is really the thing that controls the strength of interactions here. And this is RG improved, and RG improvement really means look for VF and plug in the running value of the Fermi velocity, something like that. And so this AC conductivity is corrected by logarithms. And since this number is of order 1, actually 2, I mean it has a quarter in front, and this is also a quarter, so that 2 is reduced to 1/2 roughly. This logarithm should be significant.
Sorry,
Yeah?
this is a perturbability calculation. Does it compare very well with actual experiments like value of conductivity if you calculate?
I'm about to say that it doesn't. These experiments are difficult, and they haven't really been done in the modern era of graphene with really good substrates. But to a very good approximation, the AC conductivity is just a constant. Right? Very little structure is seen in it. I mean, there's a little bit of spread here. I don't really know if the spread, like there aren't really error bars on this graph, if the spread is just due to experimental error or if it's something real at lower frequencies. But it looks like just a constant, and actually that constant is equal to or a little bit bigger than the free field value. So just dropping all the interaction terms. So here's a place where a sort of precise QED-like calculation doesn't agree with the experiment. Then in fact it agreed with the experiment better before you did the calculation. If you just take the tree level value. Okay. And so this is something also that should be explained. There's one other thing that one could do here. One could take our model, which was this one up here, and maybe deform this 4 to large N and do a large N vector computation. Right? If N were large, N equals 4 isn't large. It's sort of again in the region where that computation isn't very good. But one can imagine it's large, and the way you do that, of course, is integrate out the fermions and get an effective action for the gauge field. And this argument is more to demonstrate how the speed of the photon could come down to the speed of the electron. And that's because this leading term basically comes from one loop in these guys, And these guys at one loop, well, it's relativistic with this speed of light. So of course you're going to get Maxwell's action with this speed of light instead of the vacuum speed of light in the effect of large N Lagrangian. And in fact the N from the N species goes in front of here. Now with strong coupling, E squared is really big. Well, E squared where we're interested in is something like 40. So actually this is small compared to this. So you might think that, all right, N equals 4 here. You might think that the photon dynamics, in a sense the electric properties, are dominated by this thing, which is relativistic with the electron speed of light. Right? If you simply forget about this part, which is the only vestige of the old Coulomb interaction. And that just says that very strong coupling somehow, the graphene layer you can think of as becoming quantum a little bit thicker. And the photons that really dominate the interaction are the ones that propagate close to the sheet and somehow feel this sort of screening. And in large N, that becomes an exact statement. But unfortunately, N isn't really large enough to make this analysis good. So it's another sort of poor quantitative approach to things.
Is this large N expansion well defined? You know, in the cases where you couple a gauge field to a Fermi surface, it's known as not.
Here it is because of the point Fermi surface. I think everything is fine here in the higher orders. Right, I mean there are higher vertices in F that are ignored and they have to come out properly, but I think just the fact that it's scale invariant will tell you that they come out properly. Scale invariant, divergence free, and so on. It's kind of nice. Okay, so large N is summing bubble diagrams, and bubble diagrams do something interesting. In fact, the optical conductivity here would just come from here and would be actually the free field value, right? As this comes from this part of the photon propagator. And so the summing bubble diagrams actually gives a free field value for the optical conductivity, which is a constant and very close to what's seen. So that is kind of interesting. And if you forget about this part, of course, it is a conformal field theory of some kind, where one could, in principle, calculate things like anomalous dimensions of operators and so on. Perturbatively, but since perturbation theory isn't good, we'll go on to something else. In fact, we'll go from summing bubble diagrams to summing planar diagrams.
That's just, are the corrections 1 over n or 1 over n squared?
1 over n. Right, it's a vector model. So they're like 1 over n. And n is 4, so it's not really very good, actually.
It's n squared.
Yeah. Yeah, in fact, n equals 4 is kind of a difficult region. Right. In 2 plus 1 QED, it's already close to the critical n where chiral symmetry breaks and things like that. So it's already strongly coupled with the 1 over n expansion. Just to see what, so I'm going to take the hypothesis that this is a conformal field theory, and I'm going to do a holographic construction. And the holographic construction, instead of summing bubble diagrams, sums planar diagrams. Unfortunately, I don't have a way to sum all diagrams. Just current technology, at least I haven't found a way to do that. That would take some imagination. Or maybe it's not actually possible in the holographic duality.
So are you going to make the model non-abelian to pick out
That,
the diagrams?
that's right. Non-abelian and take a large n limit. Okay, so that's basically it. And that, in a sense, just sums the planar diagrams. Yes?
How do you plan to take the nonlinearity into account holographically? Like,
The nonlinearity, you mean of the...
but by that I mean the non-locality, sorry.
Well, that will work out just fine. That will work out, because what I'm going to do is I'll, in a sense, I'll construct a defect conformal field theory, which lives on a 2-dimensional space that cuts 3-dimensional space in half. And then I'll have the gluons of basically n equals 4 super Yang mills, which are allowed to propagate outside of this 2-dimensional space. And they'll look they'll mediate an interaction that looks pretty much identical to this Coulomb interaction, right? And is non-local in that sense. Okay, so that part will be fine. Okay. Before I go there, just let me look at what I might expect to compute. So if I'm going to make a strongly interacting theory, that's basically these fermions plus strong interactions. So that becomes some other theory, which I don't know how to analyze in the context of field theory, but we'll, using a holographic construction, what should one expect? Well, for example, the current-current correlator, which is a diagnostic of the electromagnetic properties of the system, is pretty much fixed by gauge invariance or current conservation. And if you're describing a conformal field theory by conformal invariance, because of course the conserved current doesn't get an anomalous dimension, so this thing should go like 1 over q. In free field theory, or in the large N vector expansion, the coefficient is just n over 16, where n is a number of species. And in fact, if you put n equals 4 and use the Kubo formula, here h bar and c are set equal to 1, that actually gives this tree-level optical conductivity. Right? So it's a very simple calculation, and the fact that it's a constant is a result of conformal symmetry. So in a CFT, one would also expect it to be a constant, and then the thing to compute in the CFT is how this coefficient n over 16 is modified somehow. Right? So you would expect the same kind of optical conductivity there, just a different constant.
You're just counting the charge degrees of freedom, right?
Yeah, so n here should be set equal to 4 for real graphene, and that gives the quarter that was seen, let's see, way back here in front of here, right? The sort of tree level value of sigma. So that comes out very nicely in 1 over n. So the 1 over n vector expansion actually describes this fairly well, and the 1 over n corrections are probably small enough that they'd fit in the experimental thing. It's just that it's not a really reliable expansion. So let me go in a different direction. So let's discuss a holographic construction of, first of all, 2 plus 1 dimensional relativistic fermions, and then try and draw a relationship to graphene in as much as one can do it. And so the system chose to use is a D3, D7 system, where D7 will be a probe brane eventually, and the D3s, of course, will make up, will source ADS5 cross S5, the usual holographic background. The configuration of D3 and D7 is something like drawn in this table here. So this is the 2 plus 1 dimensional spacetime. Then D3 actually lives in 3 plus 1 dimensional spacetime, like something like that. The D7 brane, its other coordinates are over here. One of these will become the radius of ADS, and then the other 4 will be some coordinates that live on the S5 part of ADS eventually. Okay. This is chosen because it's a Neumann-Dirichlet equals 6 system. If you look in Joe Polchinski's book, an ND equals 6 system is kind of interesting. Is not supersymmetric. There's no supersymmetry left here in this configuration, but there's also no tachyon in the spectrum. The only 0 modes, in fact, are in the Raman sector. The only 0 modes of the 3-7 strings are in the Raman sector, and so the only low energy modes are actually fermions. So you produce a pure Fermi gas this way. And that's what's interesting and why it chose D3, D7, as opposed to the much better behaved D3, D5, where you have a whole super multiplet of stuff living on the defect, which might also be interesting, but I thought the pure Fermi gas was probably a more honest representation of where we want to go. You can actually see what kind of spinners you get just by looking at the Neumann and Dirichlet directions. There are 4 of them, right? So there are 4 Dirac matrices, which normally have a 4x4 representation, but then the GSO projection cuts that in half as usual, and so you have basically two component spinners. They're spinners of this SO21 symmetry, and actually they're neutral under whatever symmetry this other directions have. And so you get two component spinners, and then their degeneracy is just given by the number of D3 branes and the number of D7 branes, like that. The number of D3 branes will turn into colors. Number of D7 branes will turn into flavors. Presumably for graphene, the flavor should be 4 and the color should be 1. But we'll unfortunately have to go to the place where the number of colors is infinite and do the usual TÜV scaling. And that will some planar graphs for us.
So the number of D7 is fixed.
The number of D7 is fixed and it's small. And so this will be a probe brane construction for that reason. Okay, well, this kind of construction has already been suggested by Sujong Ray, actually quite a while ago, already 5 years ago at the string meeting in Madrid, was it? 5 years ago. Published a few years later. And so he took the simplest solution for the probe D7 brane geometry, which is basically a product of ADS4 and the 4-sphere. This is a solution when the cycle is maximal, in a sense. The 4 cycle is maximal, so theta is equal to 0, is a constant. And so that's nice, ADS4 cross S4, a nice geometry where you can do all sorts of things. And so Sujong used this to suggest a D-brane construction of graphene and had worked out a bunch of results. And unfortunately, this configuration is unstable. It's unstable because the fluctuation of this angle is like a scalar field on ADS4, and it has negative mass squared, and this negative mass squared violates the Breitenholder-Friedman bound for ADS4. The result is that these exponents here are complex numbers, and so one gets complex conformal dimensions for operators, and so that's not a very nice feature of this construction, and was regarded as a problem, and maybe one of the reasons why Sujong's paper took a couple of years to come out. It has been, however, used by these authors as an example of chiral symmetry breaking. Their idea is that this is a theory, one of those gauge theories where it breaks chiral symmetry at strong coupling. And right, this is really an infinite coupling, so you've gone beyond the place where it breaks chiral symmetry. But it's one of those gauge theories that makes sense only when you tune the coupling constant close to the critical coupling. If you go beyond the critical coupling, you get into this unstable regime, and the instability should just be chiral symmetry breaking. And it's understood in other ways. I mean, this is not supersymmetric, so the D7 and D3s repel each other. And it's just a symptom of the fact that the D7s simply don't want to come close to the D3s. And for this construction to make sense, they do have to come close. They have to come to the near horizon region.
Sorry, I mean, why is this a pro-brain thing? I mean, it looks like you've tried to get a solution really of the D3, D7 system.
Well, this is the D7 metric, right? So I've taken...
That's the induced D7 metric.
Yeah, the induced
the
D7 metric.
Of the D3.
On the background of the D3s, which I've just taken as ADS5 cross S5. Right? So it is really just, you set this to 0, it is really just ADS4 cross S4. Yeah. A subspace of ADS5 cross S5, yes?
We should have anticipated this, right? This is like the D0, D6 system in the T-dual frame, where it's non-dual.
Yeah, it's also dual to, in a rough sense at least, Sakai Sugimoto, right? D48, which is also purely fermionic, and find some way to cure the instability. And here, the instability isn't as easy to cure, or at least the mechanism is different. And the only one that I know of is to actually introduce some flux onto the brane world volume. And this was suggested by Rob Myers and his student Wappler, where they suggested one could stabilize it by taking the S4, which is all these directions, and putting an instanton bundle. So you need at least 2 branes, so you have at least SU2 on the world volume. And actually this instanton bundle is a fairly ugly thing. It's some kind of fuzzy instanton, which isn't known explicitly and is not so easy to deal with. And a very nice suggestion by these authors was that you could do the same thing with abelian fluxes. And in fact, in both cases, if the instanton number is big enough, or if the abelian fluxes are big enough, it actually makes the thing stable. Stable at least to small fluctuations, in that it lifts up this mass of the scalar above the Breitenholder-Friedman bound. In this case, this is still, in a sense, a maximally symmetric construction, in that you still have an S4 over here. In this case, however, with abelian fluxes, you have to do something different. What you do is you take the 5-sphere and fiber it as two spheres, fibered over an interval like this, and then the abelian fluxes are put on these 2 spheres. So that means these 4 dimensions are taken as wrapping 2 spheres, which have Dirac monopole fluxes in them. And then again, if the flux is big enough, actually if either of the fluxes through either of the spheres is big enough, one could be 0, in fact, that actually stabilizes the system to small fluctuations. And the stable system is what I'm interested in, because of course I want to study a CFT. I don't want to study a system with chiral symmetry broken way off in the unstable supercritical regime, in a sense. And so this will be our starting point. And really all we added to this very nice construction is a careful analysis of charge conjugation and parity symmetries. And that's basically because our graphene system is charge conjugation and parity symmetric at high energies. And so one would like the system to be like that. And so CNP symmetries actually are a little bit subtle here, because the mass term for the D3, D7 string, which comes from the possible separation in this last direction, should be parity odd. Right? 2 + 1 dimensional mass terms for fermions are pseudo-scalars. Should be parity odd, so somehow parity is formulated so it reflects this dimension as well as reflecting one of the spatial dimensions. And one can show that that's indeed what one has to do to make the problem of embedding the D-brane, which is basically minimizing Born-Infeld action and the West-Zumino actions, to make it parity symmetric. One has to formulate parity so it actually isn't really parity on in the type 2b string theory, which is already chiral in a sense. You need 2 orientation reversing isometries, so if you flip this direction and this direction, that actually does it. Makes the full problem parity invariant. And charge conjugation was similarly a little bit subtle with background fluxes, which nominally break the symmetry. So some space-time transformation had to be added to charge conjugation. But indeed, one could do it and formulate it in a CNP invariant way. Parity actually is formulated to reflect this dimension. That interchanges these 2 spheres. And so the parity invariant construction actually has the fluxes on these two spheres equal. And the parity invariant point is where their volumes are equal, which means psi is equal to pi/4, sort of halfway across the range of psi. Okay, so the embedding problem for the D7 brane is extremizing this action, where I've written the ADS5 and across S5 coordinates that are used this way. There is parity and charge conjugation invariant solution, a very simple one, which has a world volume metric, just ADS4 cross S2 cross S2. It looks something like this. A peculiarity of the solution is that this extra dimension Z is actually excited here. It depends on R. That's because in the West-Zumino terms here, there's a source for Z, so it has to be non-zero. That R dependence, well, if you make this R dependent, it changes this term in the brane, in the world volume action. And in fact, effectively what it does is simply changes the radius of curvature of the ADS4, so it isn't equal to the radius of curvature of ADS5 anymore. In fact, it's a little bit bigger than it, so this ADS4 is a little bit flatter. In a way you can think of as the ADS4 has been stuck inside ADS5 a little bit bent, sort of sideways, so a flatter space fits. And flatter just, in a sense, dilutes this Breitenholder-Friedman bound. It makes it less stringent. And so if the flux is big enough, in other words, if the curvature is big enough, so this is the bound on the flux that you need, this seems like a stable solution. So flux is bigger than this funny number, 23/50ths, which I have no understanding of. This thing is stable. And so this is the solution, which is conformally symmetric. The field theory it describes is a kind of a strange one. Okay, I'll go quickly. Probably it's going to be 5 instead of 2. It's kind of a strange one because of the flux on the brane. So if you think of our three-dimensional space as this square, what we've constructed is a space that's bisected by a sort of two-dimensional membrane. On that membrane, that's where the fermions live. In the bulk outside of the membrane is n equals 4 super Yang-Mills theory. Because the flux on the, in a sense, it's an instant-on flux on the D7 brane, what it does is it's like the D7 brane absorbed a certain number of units of D3 brane charge. And so it forms a boundary between two regions where the D3 brane flux is different. And the D3 brane flux, of course, sets the rank of the n equals 4 gauge group. So it separates regions where the n equals 4 super Yang-Mills gauge group has different rank. It's a challenge to construct an effective Lagrangian for this theory, actually. The fermions that live on the boundary should transform in the fundamental representation of these gauge groups, where basically with the same set of indices, just a subset for this one, n plus k indices, and then only n of them transform under this gauge group. So it's a little bit complicated. One could, in principle, I believe, construct it by, in a sense, Higgsing this one down to this by some sort of condensate. And then the fermions would couple in a certain way to the condensate that makes them transform properly. The fermions that live here, they interact by exchanging gluons in the bulk. Those gluons have this 1 over r squared or 1 over r potential, just like the Coulomb field in graphene. And solving the large n, what we're doing here is basically solving the large n planar limit in strong coupling, which means summing planar diagrams for the gauge theory, effectively. And large n, n is much bigger than k, so it's barely noticeable, actually. Diagrammatically wouldn't be noticeable, but that's because k is like the number of Dirac monopoles squared, which is much less than n. So it's barely noticeable, but still has a non-trivial effect when you go to strong coupling. Some of the peculiar features of the theory, if you look in the ADS radius direction versus z, remember this variable z should be turned on here and goes something like 1 over r. Well, this is the only solution that's compatible with scale invariance. In a sense, if you interpret the radial direction as being energy resolution, as you go from the UV to the infrared, it looks like the boundary between the two spaces moves. So you have to think of this as a rather fat brane. And maybe intuitively you think of it as a boundary between media of different densities. And so as you back off the resolution, in some sense the boundary looks like it's moving. In any case, that's what happens here. So it's a rather wide solution. If you put a density or a magnetic field or changes in any way at low energies, it actually cuts off this thing at some, this actually enters the Poincare horizon before it goes to infinity. One can calculate the current-current correlation function. Standard holographic technique, take Maxwell equations on the brane world volume and solve them. With some boundary data, extract the quadratic form in the boundary data, that's the current-current correlator, and it comes out something like this. So as you might remember, this makes a prediction for the AC conductivity, which you can extract just from the coefficient here. That looks something like that, which you should compare with a free field value like this. F squared here is the order of a half, which actually makes these two numbers spooky close to each other. Right? This is something like a quarter e squared, and this, if you write f squared as a half, is something like a third. So these numbers are really rather close to each other. So we've gone from coupling constant equals 0 over here to coupling constant equals infinity and just summing planar diagrams over here, and it basically hasn't changed this number. Well, there are some things that do change, and I've run out of time, so just let me be very quick about them. If you put a charge density in, you can find a solution that has charge density. You have to excite a world volume gauge field that looks like this, and then the world volume metric is modified basically by a term that looks like this, which at large r, of course, is the UV, goes back to the other system, and at small r, this actually goes to 1, this factor, so it changes the ADS radius as you sweep from r equals infinity down to r equals 0. That's saved from instability by the fact that you have to use the open string metric with a gauge field to analyze stability. So here one can calculate the chemical potential. This Q, the parameter here, is like the charge density. One could calculate the chemical potential and then solve for the charge density in terms of it, and you get an expression something like this, which, if you plug in numbers here and said f squared equal a half, looks like this. And one might compare this to the free field value, and now these differ quite a bit because this actually has a factor of the coupling constant in here. And for graphene, if you just take the most naive estimate and this fine structure constant that we estimated at being 2 to 3, and so on, for graphene, lambda should be about 40, well, 35 to 40. So 1 over lambda expansion you think is pretty good. Lambda 35 to 40 means root lambda is about 6, and so this is 0.02, which is somewhat smaller than this, right? And so that's somewhere where things differ quite a bit. And this isn't really an easy thing to see physically, but this relationship, there's an old actually theorem due to Fradkin, I think, the Russian Fradkin from the 1950s, says if you take a derivative of rho by mu, you get the Debye mass, or the inverse Debye screening length. And so one should be able to see this difference in the Debye screening length, which is something that should be measurable somehow. I don't know of any place that has been measured, but it would be interesting, in fact. Here this curly b is the Euler beta function, so these numbers are all known. And it is, let's see, this inverse Debye screening length is smaller than this by about a factor of 4. So the Debye screening length, unintuitively at strong coupling, seems to be longer. Right? Strong coupling seems to screen less here. One other thing one might look at is magnetic properties. So introduce a magnetic field. That's done again by finding a solution that looks like this with an explicit magnetic field in the background. Metric again looks like this, which goes from the same old CFT at large r to one where this factor is actually 1 at small r. The vacuum energy density you can compute just from the Born-Infeld action, looks like that. From that, by taking a derivative by b, you can find the magnetization of the system. Graphite and graphene turn out to be highly diamagnetic, and that, in fact, you find here. It's kind of interesting that this D brane is diamagnetic, first of all. It's almost a surprise that it agrees that well, never mind the quantitative part of it. But if you take this derivative, the minus sign here tells you it's diamagnetic. This is again Euler's beta function and a bunch of stuff that's more or less known. And it comes out to a number something like this with a lambda to the quarter upstairs. So this is a fairly mild lambda dependence. The lambda to the quarter is probably of order 2 or 3, something like that. And one might compare this with free field theory, say. So free field theory needs to be regulated. So Landau levels are given like that. And the vacuum energy is something like that, a sum over Landau levels, which diverges. And well, in my naive way of treating this divergence, I just use the zeta function, which is something one can look up on Wikipedia, and you get something like this for the magnetization at the end of the day. It looks like that, where this n should be set equal to 4 for graphene, and similarly the n up there should be set equal to 4. These numbers are identical, and again, this is something of order 2, so this predicts a somewhat larger diamagnetism than the free field limit. And this diamagnetism there have been a lot of magnetic experiments in graphene, but the diamagnetism is always considered a background that they subtract out. And I've been pushing experimentalists to take another look at it because it is very diamagnetic, and I think it is somewhat more diamagnetic than what you'd calculate from free fermions. And so this is another thing that can be checked, and will be checked very soon, whether the diamagnetism is bigger, smaller than the free field limit. And in fact, by in a sense varying the environment of graphene, one could vary the coupling constant and in principle see if it goes like this. And actually even the prediction of conformal symmetry, the magnetization should go like root B, is already interesting and hasn't really been checked. What the condensed matter physicists do is they don't actually calculate this. They calculate the susceptibility, which is another derivative of this by B, and then set B equal to 0, and they notice that that diverges, and then they sort of stop there. And this prediction of conformal symmetry is something that would already be interesting to check experimentally. And I think will be done very soon. Okay, well, I better conclude. There are a lot more things one could say about the conformal field theory one found here, but I think I've sort of said the interesting things in the experimental realm, that if you take seriously this model as a model of graphene, it actually makes a few predictions for you. First of all, it predicts that the AC conductivity at strong coupling and weak coupling are almost the same. That actually agreed with the sum of bubble diagrams in the large N expansion. So now the sum of planar diagrams, or the sum of bubble diagrams, or forgetting about diagrams entirely in free field, just using a free field limit, give more or less the same AC conductivity, which is interesting. And agrees with experiment, by the way. And then these other two things, the screening length and magnetization density, are predictions for what the sum of planar diagrams, at least, predicts for this model. And with that, I'll thank you.
Time for a very quick question.
Are there any experiments at all that suggest there are interactions?
Sure there are. In strong magnetic fields, there is some symmetry breaking seen, first of all, and there also are fractional Hall states. So you can't have either of those without interactions.
This magnetic catalysis in the magnetic field, this happens for arbitrarily weak interactions. Is that right?
That does, that's true.
The fractional Hall states.
But fractional Hall states don't. Unfortunately, Landau level physics is very difficult to see holographically because we're expanding around strong coupling. So they don't really have anything to say about quantum Hall from this point of view. That's one weakness of holographic constructions. Right? Infinite coupling means infinite mixing of Landau levels into some big continuous band. And so Landau level physics is not accessible this way.
Thanks, speaker again, since I'm getting on.